Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Hello everyone. In this video I would like to share with you some of the primary results I have obtained during the last week of my research. I have built some components of my automation toolbox that is intended to be used within Simulink environment, and it is actually utilizing the Simscape features. As you can see here is the implementation of the simple DC power supply, where we can specify the desired DC voltage, whether it is 24 volts or 12 volts based on the desired circuits. And here we have some of the basics some of the basic components actually appearing in typical relay logic control circuits, or abbreviated as RLC circuits. Here we have a normally closed push button, and this is a normally open push button. This is a DC coilover relay or a contactor, and here we have the associated normally opened contacts of the relay K1. As you can see, they are actually holding its name, and this is a representation of the lamp, and this is the operator interface. This implementation deals with the Simscape, since we are interested in analyzing and assess the performance of the designed or built RLC circuits. As you can see here, while we can use the features embedded within the Simscape modeling features in terms of the electrical signals. So for example, if we hit the simulate or run button, we can observe now the amount of current drawn within this circuit. And once we hit the start push button, now we close, or we establish a closed path between the positive terminal and the negative terminal through the DC coil, which get energized, and its associated contacts are actually flipping their states. If they are normally open, they get closed, and if they are normally closed, they get opened. And as you can see here, we have a parallel connection between the S2 and one of the normally open contacts of the relay K1. And once we hit the start push button, the K1 get energized and the associated contacts flipped, and there is a closed path as a result between the positive terminal and the negative terminal through the lamp, and that's why it gets eliminated. And if we would like to turn it off, so we need to push the stop push button such that we interrupt the current flow, and as a result the DC coil get de-energized and the associated contacts will return to their initial state, and as a result the lamp will get turned off. So this is one feature. You have observed hopefully that the amount of current drawn within this circuit it's almost 3 amperes. So now we stop it, and let's try another connection, maybe instead of this parallel connection. And this actually helps students examining and playing around with the circuits such that they understand and analyze the performance of the built RLC circuits instead of just imagining what is really going to happen or should happen. So now if we make this connection instead and hit the simulate button another time, and we start, we need to stop it since it actually preserves its previous it actually holds its previous states. So now let's come back to the previous connection and hit the run another time and turn it off. So now we can see the coils are actually disconnected. Now let's make now this connection and hit the simulate button another time, and now let's hit the start push button. As a result, there's a closed path comprising S1, S2 through the coil K1, and K1 coil get energized and associated contacts flip their states, and since they are normally open, now they get closed, and there's a path parallel to S1, S2 passing through K1, and the K1 is still energized, and the lamp as well gets eliminated. However, using this connection, we are unable to switch it off, since we don't have any kind of control over the current passing through this path. So let's hit the S1 push button. As you can see here, we are unable to stop it. Okay, so now instead of doing so, imagining what will happen if such a connection is established, now we can simulate it using the features of the developed Toolbox and Simscape features. Now, if we imagined doing this connection instead and hit the simulate button another time and we hit the start push button, now imagine the amount of current drawn, if you can notice. Okay, why is that? This is because of the protection of this cute element. This is the fuse. Okay, so now let's try eliminating this fuse and run the simulation another time. Okay, now once we hit the start push button, now we can see there's a closed path and alternating behavior of the relay and its associated contacts, and the lamp is actually flashing. And notice the amount of the current drawn. It's almost 800, which is too much, in fact. And this can be actually justified by the fact the contacts are initially disengaged or opened, and the coil is de-energized. Once we hit the start push button, now there's a closed path comprising S1, S2 through coil K1, and once K1 gets fully energized, its associated contacts will flip their states, and K1 will actually close, and it will establish some kind of short circuit path. And that's why we have a huge amount of current drawn using this configuration. And the alternating behavior can be justified by the fact once the coil is energized and the contacts are closed, there is a short path, short circuit path, and this will bypass the coil itself, and as a result it will get de-energized, and the associated contacts will disengage, and while we are pressing S2 push button, now there is another path. We will come back to the initial path comprising S1, S2 and the coil K1, and the cycle goes on and on as long as we are pressing the push button S2. Now, if we introduce the fuse into the circuit and we hit the play another time, and once we make this arrangement, as you can see here, now the circuit actually will never function another time, since now we have no current passing through the circuit since the fuse has blown. And this, in fact, is some of a simple that shows the potential of the developed toolbox I was working on during the previous week. So I additionally built a number of components appearing usually in RLC circuits, such as delay on, delay off timers, counters, and overloads, and three-phase contactors. And this, in fact, actually was intended because of the feature of the model-based design possessed by the Simulink environment, since we can deal with multi-domain systems such as mechanical and electrical, pneumatic, and electronics as well, so that we can simulate DC circuits, AC, whether it is a single phase or three-phase circuits. Another example I have also prepared. This is the programming of a PLC device using what is called ladder programming language. Here you can see here I have prepared three tasks. The first task is responsible for the health monitoring, and the second task is responsible for the error diagnosis. And here we have a scheduler. Even though it appears with a simple implementation, it can get more sophisticated and complex as well. This depends on the application and the needs. And the third task, representing the main task, actually is appearing right here. Here you can see we have the contexts associated with the inputs. I have worked with mainly 6 inputs and 6 outputs, and those are the open contexts associated with the relays. Here we have K1, and here we have the timers. This is a delay on with a preset value of 2 seconds, and this is the delay off with preset value of 10 seconds. And those are the outputs, and this M1 actually represents an internal memory location in the program, and we can utilize, in fact, the results appearing here. Here I have simulated a simple example where the input one is activated using this signal, and input 2 is activated using this signal, and the same can be said about the input 3. So now here we have a scenario, and we would like to examine the behavior of the developed ladder diagram based on that. As you can see here, this is a special block I have introduced into the scene, and it is namely responsible for enabling or disabling the associated ladder diagram. And as you can see here, as an additional feature, I have introduced to the ladder blocks, which are usually appearing in the automation field and PLC programming software or IDEs. I have here introduced an additional output for a Simulink signal that can be used, for example, to enable or disable other tasks, and also can be used to capture the behavior of the associated component, or also it can be introduced with other components in order to expand the functionality of the developed ladder diagram, such as if we would like this coil status to be affected, or to affect, in fact, another part of a real system appearing somewhere in the plant or in the workshop. We can here use the OPC read and OPC write functions. We can also use RC232 in order to establish simpler serial communication, or we can use as well the UDP or TCP/IP protocol in order to communicate with other parts, maybe in a complex model or in a real system or emulator platform. So now let's hit the start push button and the start button, and let's examine the behavior of the ladder diagram, as you can see here. Okay, so using this scenario, there's a planned fault that will arise some certain condition. In order to see this, I will enable the errors, and let's see together how this will affect the behavior of the root nodes, and how the corresponding components will respond to that. You can see here now, since this is a root node in red, now the associated ladder circuit is deactivated. In order now, just we can see the response. As you can see here, this is enabled. Now this is the instant of time at which the error occurs. Now you see all of the outputs are disabled. So now if we are resetting this error and playing it another time, we observe the behavior of the same program. Okay. And once it's done, at the scope to see the behavior of those signals. So this is an additional feature of the toolbox I was working on. As a final example, this is a more sophisticated example that actually shows you, hopefully, what I have in mind while I was developing this toolbox in the first place. Here I have used a three-phase power supply. Here we have L1, L2, L3, and this is the neutral, and this is the power earth or the PE, and here we have the DC power supply. This actually helps the student imagining how the DC power supply is actually connected to what is called the power circuit, because usually whenever we are presenting the concepts of RLC and PLC, we need to introduce some terminology associated with the control circuit and the power circuit. And here we also can have the mechanical systems and the pneumatic circuits, etc. So now let's focus here. Here we have the RLC components. Those are the normally closed contacts associated with the overload. Appearing here, we have a three-phase motor, which is connected through an overload, and there's a contactor, three-phase contactor, and this is the motor, and this is actually port representing the rotational free end. We can also build other mechanical systems. As you can see here, we can utilize the features of the Simscape library or toolbox and develop more sophisticated or complete systems, so that the student will have the complete exposure of the design cycle instead of just focusing on the electrical aspects of the design process. Here we can deal with gearboxes and inertia and so on and so forth, so that we can model. If we are skillful enough, we can model sophisticated mechanical systems such as conveyors or pick and place mechanisms or the like, so that we can elevate or we can actually expand the field in which the student actually needs to do the programming skills and design process. Here we have a simple PLC device. It consists of 6 inputs and 6 outputs, and those outputs are actually built as relay outputs. They have changeover contacts or outputs. Those connections are actually representing an open circuit connection. Here we have three relays or contactors. As you can see here from the diagram, here we have R1 is associated with this. So this is actually a DC coil of a contactor rather than a simple relay. And once it is energized, its associated contact will engage or disengage based on its control signal, and the three-phase power supply will be supplied to the three-phase motor, and here we will have some kind of electromechanical interaction. So you see here we have the previously seen RLC components. Those are the two normally open push buttons, and this is normally closed push button, and those normally closed contacts associated with the overloads. Here I'm having 3 circuits representing 3 conveyor belts, but I have commented those two in order just to facilitate the simulation time. And as you can see here, all of those connections are actually electrical, and here we have the fuse, and this actually gives us a more realistic picture that we are unable to have if we are using other approaches, I think. So now, double-click this PLC code, PLC block. I have actually equipped this block with the ability of dealing with MATLAB code or Simulink model or ladder diagram. So if we are choosing to deal with MATLAB code, we hit apply and we can open the source code. As you can see here, we have the inputs and the outputs, and here we are actually entering our code. So this is the control logic. So now simply it says if the input 1 is not activated and I4 is activated, so we need to the first output that is associated with the first motor to be on, and the other activation rule, if we have I3 on and I5 on, so the second output will be on or true, and the same for the third activation rule. If I6 is true, then the sixth output should also be true. So this is a simple implementation of of the control logic. As you can see here, those are actually the states of the inputs and outputs, and they are get actually updated during the simulation runtime. So now let's hit the run push button or the run button to start the simulation and observe the behavior. So this is actually the associated user interface. So here, once we hit S1, you observe now how the states are actually updating and the corresponding logic is actually taking place. So let's push S2. Now we are deactivating the first output, and as a result, the contacts are disengaged and the motor will stop, as you can see in this region. Okay, if we just preset the overload value to a certain current value that is allowed to pass through it. So if it is exceeded, then the associated contact will actually change its states. Instead of being normally closed, it will open, and this will affect indeed the control logic. Okay, as you can see here now, if we hit S3, now the second output will actually get actuated, as you can see here. Okay, so now we change the control logic based on the Simulink model, and we open it, and you can see here I have just used the logic gates in order to introduce the students to the control logic using digital gates, so that they implement whatever they like or the intended functionality using simple gates, or maybe they can use also the various Simulink available components or Simscape components. They can use as well the state flow components to build their own control logic. And the third option is to use the ladder diagram. Once we can open the programming model, and we can see here this is the OPC. Okay, so now if we put them side by side, and we allow the simulation to take place, okay, and we hit the run button, you can see here now, based on the signals. So in order just to give it more time, let's put it as infinite instead. Okay, and just change both of them to infinite. This is already infinite. Okay. So now let's hit the run button, and let's observe the behavior of the simulation. Okay, so it's based on the inputs, we are actually now activating. You can see it. I'm just here. I'm pressing S1. I need to work with this one instead. Sorry for that. Here I need to press the simulate button. And you can see here once I'm pressing S1, as you can see here now, the output actually gets deactivated, and as a result, the contactor gets disengaged. Now, if I'm hitting, so now in one of the issues I'm working on recently is trying to optimize the performance. As you can see here, during the initialization, I'm having some latency, and I need to figure out why this is actually happening. So now let's see, press S2. Okay, now you see the first input, and the first output actually gets updated. Here I'm pressing S1. Observe the status of the inputs and the outputs in both the PLC screen and the ladder diagram simulation part. Okay. So now I'm removing the mouse, and I'm trying to push S2 instead here. Okay, now S2 is pushed, and now the input is updated. Now we are waiting for the output to change. So this is actually needs to be consistent with the logic we are actually developing. But I hope now you get the idea. Okay. This is what I have for now. I will be working more, inshallah, on improving the quality, the simulation, and the performance of the presented components, and hopefully I will be able soon enough, inshallah, to introduce more realistic power circuits or systems, and to show how the multi-domain modeling process can actually benefit the developed toolbox, where the students can actually introduce whatever machine they are working on into the scene, and to connect it to the control logic, and make a kind of assessment for the designed control logic. جزاكم الله كل خير. بارك الله فيكم. السلام عليكم ورحمة الله وبركاته.